everyone, thanks for coming. Today we have Clare Dobbs from the University of Exeter. She's a senior lecturer there. Today she's going to talk about the evolution and formation and so on, and star formation in galaxies, well, the evolution of clouds and the clusters that form within them and spiral galaxies. And Clare is an expert in everything related to the formation and evolution of GMCs and star clusters. Also spiral structure in galaxies. So for example, how does the dynamics of galaxies themselves affect the formation and dissolution of GMCs and star clusters? And yeah, I'll let you start in it.
Thank you very much.
Oh, and there's still a few spots in your schedule today, so feel free to add your name.
Yeah, so my work focuses on running models of galaxies and trying to understand star formation from a galactic point of view. Well, one of the main problem of studying star formation on galaxy scales is the vast range of scales between galaxies and stars. So I've just shown here some of the objects, the spiral arms, the clouds that we see on the different size scales and their relation to star formation. So if we look at a spiral galaxy, we see most of the star formation occurring in the spiral arms. So that suggests that we can't necessarily ignore the galactic scales when we consider star formation. If we zoom in further to say something like a Milky Way spiral arm, this is what we see. We see clouds of gas along the spiral arm, some of these forming lots of stars. If we zoom in further, we might see something like Orion, and if we zoom in further, we start to see individual stars. There's many orders of magnitude between these different objects. So much of my research focuses on these types of objects, giant molecular clouds that sit sort of in between galaxies and stars and sort of make a good sort of reference point between the two scales. So here's just some of the main questions that I and other people are trying to address. What determines the overall star formation rate in galaxies? Here's a very famous Kennicott plot showing points for individual galaxies. Here's again a very famous plot, but now taking subregions of galaxies rather than measurements for the whole galaxies themselves. And you see it obeys a very well-known power slope, but also the star formation rate is a factor of about 1/100th or so of what you might expect theoretically. So these star formation rates are lower than what you might expect just from theoretical arguments. Much of my work focuses on how do GMCs form. I'm going to be talking a bit about how long they survive, and also a question is what processes disperse GMCs, what gets rid of the gas and just leaves a cluster. So I'm sure many of you already know all this, but in case there's people that work in different areas, giant molecular clouds are where most star formation occurs. They're observed to have high velocity dispersion, suggesting they're turbulent. Only a very small fraction of the cloud actually forms stars, and most appear to contain ongoing star formation. If we look at this, so this is a galactic giant molecular cloud. We can also now make observations of GMCs in other galaxies, particularly with ALMA, but before ALMA, the PAWS team made this CO map of M51. As you see, most of the CO and the molecular clouds are associated with the spiral arms. So one question I'm going to talk about at the beginning of the talk is the lifetime of giant molecular clouds. So different ideas about lifetimes. So I'd say probably the older idea is that GMCs are quite long-lived. So some of the rationale for that was because if you look at M51 or the inner part of our galaxy, there's a lot of molecular gas between the spiral arms, so people think that the clouds just survive a long time between the arms. Connected with long-lived clouds is the idea of collisions of clouds. If they last a long time, then it's possible for them to undergo collisions. Some groups suggesting that this triggers star formation. And then in the last sort of 20 years or so, other people have focused on short-lived clouds, where the clouds are in a process of gravitational collapse, so their evolution occurs very quickly, star formation occurring, and often discussed in relation to sort of quite local clouds, possibly that have been triggered by recent supernova events in the region.
The long-lived clouds are entirely an observational error made by very loud people who insist that their observational errors are not in fact errors.
Well, I'm going to argue for short-lived clouds. So I've been following the evolution of these clouds in galaxy simulations. So I use the smooth particle hydrodynamics code. I only model the gas to reduce the computational time needed for these simulations, so everything else is modelled as a potential, so that includes the galactic halo, spiral arms. The main simulation that I'll show you to begin with has 8 billion particles, so each has a mass of 300 solar masses, self-gravity and cooling and heating of the ISM, and I also include H2 and CO formation. For these simulations, there's also stellar feedback. Here it's a fairly simple prescription based on supernova feedback. Energy stellar feedback is assumed to occur once the density of a region exceeds a value. For most of these simulations, it's 500 particles per centimetre cubed, and that gas is gravitationally collapsing. Energy is inserted according to a Sedov solution, which I think is 2/3 kinetic and 1/3 thermal energy. This can be added instantaneously or spread over time. So most of the models I show is instantaneous.
Sorry, is this supposed to mimic supernova feedback or jets from Exeter or whatever?
It's nominally supernova feedback. Other processes like winds and may have similar amounts of energy to supernova feedback, and you could also put into the models crudely by just doing the same thing, inserting energy. But nominally it's supernova feedback. And there's an efficiency parameter here. So to calculate we calculate the star formation rate from particles within a couple of smoothing lengths from the mass of those particles. There's an efficiency parameter which allows for that you wouldn't expect all that gas to be converted into stars. And the 10 to 51 ergs is, of course, from a supernova. Yeah, and in some of the calculations that I show later, the densest particle is converted into a star particle.
So is the feedback a disruptive process in this model, or does it do both, or does it enhance star formation? I wasn't clear from what you just said.
It's primarily disruptive, I would say. So later I do some sort of shells, and we could investigate whether that triggers star formation. I actually had a summer student work on that, but they didn't really get that far, so that could be something to look at. So if I run this is a movie of the disk. The blue and the yellow colour scale is for molecular gas. So to begin with, the gas sort of just undergoes sort of gravitational collapse before feedback occurs until you, just on the bottom one as well, and it then evolves to something like a steady state where, I'm waiting for it to run again, where you've got gas flowing through the spiral arms. It undergoes gravitational instabilities, cooling instabilities, and cloud-cloud collisions. In a model like this, it's quite complicated because you have all those processes happening at the same time. But we have random models where we just think turn off gravity or turn off cooling and see what happens to the gas. And this is the vertical plane, and the feedback is able to lift some of lift material above and below the plane of the disk, some molecular gas lying above and below the plane of the disk. Without feedback, this would be a very thin, which is not in agreement with observations. So we can then try to extract clouds from these simulations. I've just used a simple clump finding algorithm that divides the grid into cells and then selects cells above a given surface density. Surface density shown in the captions here. We can look at things like the mass distribution of the clouds, with real parameters, and their rotation. So we found, for example, that the clouds appear to be both bound and unbound, and I think this agrees with various observations of both external galaxies and within our galaxies. And we also found that when the clouds, some of the clouds have retrograde rotation, which means that they all orbit the galaxy in with the same rotation, but the intrinsic rotation of some clouds is in the opposite direction to the rotation of the galaxy. And this is also something seen in observations. So generally, we get realistic cloud properties out. I would say though that if you don't include, if we didn't include any feedback, then we started to get properties that didn't agree with observations. So for example, we started to get a population of very massive clouds that were very long-lived, and all our clouds had very low viral parameters without any feedback.
How big were your cells? Are you resolving clouds, basically?
Yes, it's resolving GMCs, yeah, but not things smaller than GMCs. And then to look at the next part is looking at the lifetimes of these objects.
Do you compare it to like the core mass function? Or sorry, the cloud mass function? Similar slope?
Yes, it's fairly similar slope.
Charlie, there's your answer, because it's 546, 16,
But you don't have magnetic fields, do you?
No, so I forgot to say that there aren't magnetic fields in these simulations. So we then wanted to look at the lifetime of these clouds. So I started by taking just one particular example and following its evolution over time. So I highlighted this particular example. It's a 2 × 10⁶ solar mass cloud. And with SPH, you have the advantage that you can trace the particles backwards and forwards with time. So this shows the sort of the backwards evolution, if you like, of where this cloud came from. The coloured blobs show different clouds that then combine to produce this the cloud that was selected. But there was also diffuse gas as well that went into this cloud, and that's in the white dashed lines indicate basically the locus of where the more diffuse gas came from. There's a couple of clouds here that are in these sort of kind of filaments in the interarm region that are entering the spiral arm and then go in to make this massive GMC. And this shows what happens to this cloud, the later evolution. And in some ways it's a bit of a sort of reverse or mirror image of how it was formed, just because of the rotation of the galaxy and the shear. So now this object is being sheared out into a sort of a long spur, and the clouds, well, this is separating again into smaller clouds. So this is dispersing by both shear and feedback, and we established that by, for example, turning feedback off and finding that it didn't disperse, and also calculating the rate of shear x radius to show that shear was affected.
That's 20 million years from the top left to the bottom right.
Yes, yeah.
That's it.
No, I say it depends a bit on mass. So I find that the more massive ones live longer. But then also, it becomes quite confusing, because if you're talking about the lifetime of this sprint cloud, for example, it was once part of a more massive one, so, so it's not completely straightforward. But then how do you compute a lifetime from this? So there's no real obvious way of defining a lifetime, but what we did was to take the time over which there's at least half the gas in this, where is it? This selected cloud in other clouds at earlier and later times. So, for example, if this red blob is half the mass of that, then that would be the end of the lifetime of that particular cloud. And we did that for all the GMCs, and we looked at how that compared with the crossing time of the cloud. And although there's quite a lot of scatter, partly because if you some of the clouds are sort of a bit more spherical and some of them are quite filamentary, so that was at least part of the scatter. But there is some rough agreement between the actual lifetime of the cloud and the crossing time. And so we get, I'd say, relatively low lifetimes, so about 5 to 10 mega-years. For them, these are more massive clouds up here that live longer. They're sort of 10 to the 6 solar mass clouds. But our results are in general agreement with other observations and simulations. We may have chosen a slightly more restrictive definition of the lifetime, because the gas has to be the same gas, whereas if you're just looking for any cloud that has some of the gas in the chosen cloud, you might have a slightly longer lifetime. But I would say that the actual cloud formation and destruction process, here you can see it's sort of really going on for at least 40 mega-years. You've still got this large spur here that's related to the cloud at 250 mega-years. Yeah, so I'll just go through this quickly, but as I mentioned at the beginning, it's thought that clouds may collide and that may trigger star formation, and in a fairly recent paper we looked at that from the simulations, again using the advantage of SPH being able to trace the particles, being able to trace a particular gas in a particular cloud and where it's come from, and we formulated this description for the possible outcomes of cloud interactions, or what can happen to a cloud between one time step and the next. And we introduced these fractions, so the fraction f indicating the fractions of gas in clouds at the previous time step, and g indicating the fraction of gas in clouds at the next time step. And for those, you can have these definitions for whether the clouds have merged or whether they split, whether you've got new clouds that have been created, or clouds that have been destroyed between two successive time steps. Well, we had many plots showing the different probabilities of these, but for collisions, which I'll just talk about here, we found that they're quite frequent. So we found, I think, about one collision every 8 megayears or so. So given our lifetimes of sort of 8 megayears or 20 megayears for the more massive clouds, that suggests that clouds might undergo 1 or 2 collisions during their lifetimes. And this again is consistent with other work. The collisions of the most massive clouds were very infrequent because there's just so few of the very massive clouds. So this has been suggested to perhaps produce young massive clusters. So it could be possible, but it would be a very rare event. We have shown in previous work that cloud collisions can contribute to producing GMCs, and also derived a measure of the spacing of GMCs along the spiral arms in the event that GMCs are formed by collisions. But we found, at least in these simulations, that the cloud collision wasn't having a big impact on the gas itself. So you might get two clouds merge, but it didn't really change the gas very much, like for example making it much denser. I can just show that here, where there's gas after the collision in different orientations, and the clouds haven't really changed after the collision compared to before. There's no sort of really dense peaks in the gas that weren't there previously. But, well, I suppose one reason might be that the velocities of the colliding clouds is quite small. I think in the examples shown where they think that colliding clouds might have led to a massive cluster, they're a few times higher than what we see here. I'd also caution that you'd really ideally want to run these sorts of things at higher resolution to properly model the interface between the clouds colliding. So one question is, having simulated a galaxy, and we can resolve GMCs, but not smaller clouds. But are we really resolving the properties of the GMCs particularly well? If we increase the resolution, would they change? And what about the lower mass clouds? What do they have different properties, or do they just follow the same trends? So I ran some resimulations where I just selected a region of gas going in the spiral arm, and ran these at higher resolution, so that now we can get the full range of cloud masses. So now the mass of each particle is just under 4 solar masses. So this compares, this is just gas. So I should have said the simulations were otherwise the same as the galaxy simulations, but just had a slightly higher efficiency for the feedback. We ran ones with 10 and 40% compared with 5% previously. So just the efficiency change. This shows the gas between the resimulation and the original simulation. So largely it looks similar, but obviously with the higher resolution you can start to resolve more detail, the structures in more detail. So going on to cloud properties and now getting down to clouds that are 1,000 solar mass or lower, we basically found that there are similar cloud properties to before, so the resolution didn't make a great deal of difference. I'd say actually the real parameters were slightly higher, perhaps because we can resolve better the internal velocities in the clouds compared with the galaxy scale simulations. We still find both bound and unbound clouds, and we still find retrograde clouds, and that continue we find for lower mass clouds.
Sorry, so that's only as your starvation efficiency?
Yes, that's right. And with our most massive clouds, we can start to look at the internal structure of the cloud. So with 10 to the 5 solar masses, that's then 10 to the 4, 10 to the 5 particles. We see that the clouds are quite structured. Here the crosses mark recent feedback events that have blown out the surrounding gas. And we start to see something like the Larsen relation for the cloud itself. And here we've made a sort of a star formation rate plot like the ones I showed at the beginning, and so this is one where I've divided the region of the galaxy, or well, the section of the spiral arm, into regions of a size, I think it's 100 parsec boxes, and computed the star formation, amount of star formation in each box, and surface density. This is for the purple points, this is for the 10% efficiency case, and this is for the 40% efficiency case. And the crosses are from previous work by Ian Burnell, where he made similar types of plots. But those simulations didn't include any feedback. But for the ones with no feedback, they're clearly way off the observed points, which are the blue or turquoise points in these figures. So it seems that quite the high feedback is required for the best agreement with the star formation rates for these particular models.
Do you think it could also be that, because like the star formation efficiency is typically 10%, but it could also be that by raising, because you're only considering supernovae, so by raising the star formation efficiency is kind of, in a way, adding other feedback, like taking into account more energy injection?
Yes, that's one possibility, and again, these simulations don't include magnetic fields, which some people have shown also reduce the efficiency.
And are you thinking the fact that you have so much more low surface density material is due to the fact that that's not observable, or that there's a discrepancy there?
Yeah, I think it's just a selection effect. Also, the boxes that we used are smaller than the ones in the Big Eel paper. So if they used smaller boxes, they'd probably have regions that they don't detect H2. I think I did look into this at the time, but I can't really remember this well. I think they might have had some null detections in the observational plots, which is like all our points down.
There's also the big issue of how you define a cloud. We can get to that.
Well, this is just
This is
taking
just
boxes.
pixel,
Yes,
I know, for the other.
Yeah.
I actually thought I would follow up on that now. Did you select clouds via H2 or CO?
So in the ones I've shown before, so far, they're just selected on their total gas density. But I'll show you just one example later. Anna Duarte-Cabral has been making like cloud catalogues, but from the H2 rather than the total gas. So I won't really go into it here, but she has done that.
So do you track the H2 to H1 fraction in the clouds?
Yes, yeah. Well, in all the gas particles, yes. So yeah, it's just the standard equation for H2 evolution that has a rate of formation on grains term minus the dissociation term, yeah. And as well as clouds, we can also start looking at shells and filaments, which we could see with the galaxy simulations, but they were quite poorly resolved. And now you can see the feedback producing these shells, and in high feedback case, some of them open into with gas escaping above and below the plane. You can also more clearly see these filamentary features between the arms, and these have also been the subject of quite a lot of observational work as well in our galaxy, and we also see sort of long intron features in external galaxies as well. So these are very high aspect ratio. The lengths of these features in our simulations are hundreds of parsecs. This circle here just indicates a feedback event that has occurred in filament. So it's just sort of created a little breaking, but it hasn't really destroyed the filament. I mean, I suppose most of the energy is going to go out in these directions, so it doesn't have a massive impact on the whole filament.
And just because we're especially interested in that, are those filaments, when they're seen from the side, are they in the midplane?
Yes. Yeah, yes, they're... yeah, so these long filaments are actually the remains of GMCs that have come out of previous spiral arms. They've been sheared in the by differential rotation, and they're all just sort of, yeah, they're all aligned with the plane. So these ones at least aren't perpendicular to the plane at all. So one of the things I was interested in was actually whether the intron filaments could be the precursors of spiral arm GMCs. So here's just an illustration where I followed a filament over time and found how it entered the spiral arm. So these show GMCs that are already in the spiral arm. They sort of combine to form one massive cloud. But this filament here goes on to produce this object here. It does combine with other gas in the spiral arm, but it seems to be like the precursor of this spiral arm GMC.
And that's just 4 million years between us.
Yes.
Just a general question. Since you show that the lifetime of these entities is following the crossing time, they are not really entities. They are not clouds. They are just featured, high density regions that come and go all the time.
Yes. Yeah.
So why do we assign an identity to these things if they are not lasting more than the crossing time?
Because the crossing time is longer than how long it takes to form stars.
Yes, but the crossing time is the minimum time for something to change. And if they last just for this minimum time, it means that they don't exist.
You're right, but we need to count some.
But they are not objects, really. They are not clouds.
Yeah.
Like based on your results, I'm not.
Yeah,
Maybe in reality they are, but here, based on
Yeah, I agree with Alyssa that you have to call them selves, don't you?
but you can
I
call them
was-
high density transients.
And yeah, I think like the observational papers, I wouldn't class this object really as a cloud. It's it's not really like a GMC. It's got much higher aspect ratio. I mean, I don't know how, the virial parameter perhaps doesn't make that much sense, but it's got a very high virial parameter. It's not globally collapsing at all. It's just got local regions of star formation along it. And here's some work by Anna Duarte-Brau, and she was looking at the H2 CO fractions in these filaments going into the spiral arms, and this shows the H2. I think the contours are H2 on the total. No, sorry, the black and white is H2, I think, and then the contours show filaments that have been selected using the Symes algorithm. So again, this is an intrafilament, and here it is in the spiral arm. It has combined with other gas to make this spiral arm GMC. But this is H2, and she did this similar thing with CO. With CO, you just see, at least in the interarm region, you only would detect the peaks in density of this long filament. So it's mostly, or at least some of it is dark dark H2 rather than visible CO.
Does she see some of the long CO?
Yeah.
Long like filaments that you see? Those are detected.
Yes, yeah. I can't remember whether she has examples where she has got a long filament. I think she might have a few.
Yeah, but they're the widths of them are uncontrolled.
So this is just a summary of the first part of the talk, which concentrated on clouds. So they appear to evolve dynamically on quite short timescales, similar to the crossing time of the cloud. But chemically, I think they can exist for longer, because when you see these dense, relatively dense filaments that pass between the arms, that last for longer time periods. One question is how realistic our imposed spiral model is, but there's been similar work, a similar paper by Barber earlier this year, and they found sort of similar pictures of cloud evolution and similar cloud lifetimes for a dynamically evolving spiral. Cloud collisions do appear to occur and relatively frequent. They may increase the mass of the clouds, but they don't seem to have that much impact otherwise. And provided that feedback is included in the simulations, we find that the cloud properties and star formation rates are sort of in reasonable agreement with observations. So just for the last part of the talk, I will talk a little bit about cluster evolution. So this was trying to understand how clusters evolve and how this compares with the evolution of the clouds. So I'll show you, again, galactic scale simulations, and now each time a star formation event occurs, then a star particle is added. So the simulation was run first for 200 million years without including star particles, so it forms a nice spiral galaxy. and then the star particles are added and it's run for another 200 megayears. So by 200 megayears, as you expect, most of the galaxy is covered in star particles. And this just shows a stellar density map of the younger stars at the end of the 200 megayears, and this shows how it compares with the gas. Now, part of the motivation for this was to compare with observations, in particular the Legger survey. So we divided the stars into different ages. So these are, again, stellar density maps for younger stars at the top, and the middle is 10 to 100 megayears, and the bottom is 100 to 200 megayears. For doing different models, one with, I think, 5% feedback, and one with 20%. And what we found was that for all the ages, we still found quite clear spiral structure in the stars. So I think in the observations, sometimes the spiral structure is not so clear in the older stars, which I think could be because they often don't have many older stars. It could also be if the spiral arms aren't that strong, maybe they're not strong enough to retain a spiral structure in the older stars. But we tried this in both my simulations and some simulations by Gareth View that are quite different. They're with a grid code using transient spirals, and we found the same thing, that the spiral structures tended to stay even in the older stars. Another thing that we noticed was that in the low feedback case, we get these sort of dense areas and stellar density maps of quite massive clusters, and these are associated with very massive GMCs. In this case, these were objects where the feedback was where the stellar feedback is quite low, and it's not able to disperse the clouds. So the stars just keep forming, and you get a very massive cluster. But with the high feedback model, these massive clusters didn't occur. So this just follows the evolution of one of these particularly massive cluster. In this particular example, there were two sort of clouds together, two clouds that merged, and then their star particles came together. For this example, most of the star formation occurred over the last 50 megayears or so. I think this shows 100 megayears time. These stars here aren't really, these are more just random stars that probably ended up in the cluster, but really this is when there's lots more star formation occurring and most of the stars are produced. It was difficult to produce these massive clusters in shorter time scales, or at least we didn't observe clusters forming in shorter time scales. But this could be a resolution effect. So I would just say that, although I call these clusters, they're not as dense as observed clusters, just because of the limitations of the numerical simulations, the limitations given by the smoothing length of the simulation, which is just going to be parsec scales, which is similar to the size of a cluster, really. So it's difficult to model very dense clusters. I think you really need to go to higher resolution to be able to model those properly.
The red things that you see there that look like clusters, that's on much larger scales than the cluster, right?
Yes, yeah, that's
so these
right.
are not, is that what you're saying, and these are not sort of the classical sense of the cluster?
No. They're perhaps more, well, these ones are bound, but they're perhaps a little bit more like bigger associations. Yeah, it's perhaps best to call them associations rather than clusters.
Is the feedback coming from the individual model stars or regions of stars, or is it just parameter? is the feedback coming from individual stars, I guess is the simplest way to say it.
Yes, yeah.
So spatially, then, if the resolution is too low to see those stars, then you can't actually model feedback correctly, right?
Yeah, I think that's another issue that, or the same, or still related to the resolution isn't quite what you would want to model these types of objects, that you can't resolve the feedback properly either. This is looking at sort of clusters that and how long they take to disperse. So this is one of these quite fairly massive clusters that takes quite a long time to disperse. Whereas, well, again, I should say association. Whereas this is very much an association where it's completely dispersed over timescales of a few tens of mega years. So I think most of the associations that are in the simulation are this type of object. And this shows a comparison with observations, so plotting dn by dt versus the age of the clusters has been done for a number of nearby galaxies to look at how quickly the clusters disperse. So this particular one was for M83, and for the simulation, so the steepness of, if this is a particularly steep slope, that indicates that the clusters disperse quickly. So in the simulations, we tend to get a fairly steep slope, sort of at the steeper end of this. I think these are different regions here, at the steeper end of the observations, particularly. So these are different criteria for choosing a cluster. This is the most strictest criteria, which required that the ages of the stars were within a range of 10 mega years, just perhaps a little bit more realistic. Is quite steep compared with the observations. So I think this also suggests that we're perhaps not quite really reproducing the very dense clusters that survive longer, and so our clusters are thus dispersing a bit quicker than we see in observations, again probably because of the resolution of the simulations. And then I just thought I'd briefly mention future and ongoing work. So I think one of the criticisms of the feedback is that I've only included supernova feedback, and realistically you would have ionisation that acts before the supernova takes place, that we should be able to resolve in our sections of spiral arm. So my student is currently working on including that in these sort of spiral arm scale simulations. I just thought I'd show this as well. As I mentioned before, one of the limitations also is using a fixed spiral potential, whereas most galaxies don't quite look like this. So this is just a project that I've been doing recently to try and simulate M33. So M33 may be interacting with M31, but here I've just modelled it as an isolated galaxy with live stellar disk and gas. The halo is potential, but the halo, stellar disk and gas profile have all been chosen to match observations, paper by Corbelli in 2014, and we found it produced quite good, or perhaps very good, agreement with M33, suggesting that perhaps in this galaxy, unlike something like M51, that the structure can arise without interactions with other galaxies, and actually the arms labelled 1 and 2 are actually just copied and pasted from the model into the real M33. Right, so that's everything I wanted to say. So it's just some conclusions that the clouds seem to evolve dynamically on quite short timescales, a few megayears to sort of 20, 30 megayears. But we do see these filaments that survive between the arms on longer timescales. The clusters, they seem to evolve quite similarly to the clouds. So if you have a very massive cloud that's very bound, then in the simulations that seems to produce a very massive bound cluster, whereas in quite transient clouds, as you expect, just form sort of transient associations. And I had a little look at cloud collisions, showing that they are fairly frequent, but they don't, in my opinion, I don't think they have a large impact on the gas or star formation. And numerous papers have shown that there's not a big increase in star formation in spiral arms, which you might expect given if cloud collisions were important for triggering star formation, because you might expect that you'd have many more cloud collisions there and that might trigger more star formation. So I think that's it. Thank you.
Any questions? Yes.
So is the internal velocity dispersion of the clouds dominated by the energy coming in from clouds colliding with the cloud from outside, or is it from internal energy from the stars embedded in the cloud?
I think it's. I think the biggest factor is probably feedback, which could be from within the cloud. It could be from other nearby star-forming regions. If we run a model without any feedback, then the velocity dispersions are lower. I think it just churns up the gas everywhere in the galaxy.
Lower, but still supersonic?
Without feedback, I think it's sort of around the sound speed without feedback. There's some dispersion introduced by the spiral arms as well, by the spiral shocks, with or without feedback. Yeah, I think it's some feedback.
Have you looked at how quickly star formation turns on in a forming cloud?
Yeah, I think in our clouds, I've not sort of, I suppose, done any analysis, but just from looking at the movies and what happens, I think it's pretty quick.
I guess
but then there's nothing to stop the clouds forming stars.
I'd be curious to know if you have stars forming before you have the definition of a cloud, and if star formation, does it peter out as your cloud disperses?
Yeah, I've got a plot which I haven't showed here that just looks at star formation versus time for a few clouds, and it peaks at when they're most massive, and so it just looks like I don't know, it goes from there's just a little bit of star formation, then it peaks when it's most massive, and then it does like the opposite when it disperses.
So does the star formation per unit molecular mass go up, or is it just because there's more molecular stuff all in the same place, there's more stars?
I think it's the latter.
I'm just trying to understand the lifetimes that you get when you said that these clouds are sort of ephemeral because they cross in time about their age. Is that because when they get to the point you identify them, they have enough mass that supernova have gone off? Or is that because the internal velocity dispersions, when they form, are so high that gravity is not important?
I think it is both.
So when you say clouds unbound, like you saw so many clouds unbound, are you just comparing the kinetic energy with the internal energy, or are there other pressure terms?
There wasn't pressure terms. But again, if there's no feedback, then their velocity dispersions aren't high, and you end up with the gravity does become much more important. The clouds don't have short lifetimes.
Catherine?
We were tired of closing out potential with more than 2 spiral arms, like 4 or 6 or so. Does this affect the cloud lifetimes?
Yeah, actually, I started off with a 4-arm spiral potential, but I didn't think it was that realistic. I think most grand design galaxies are 2-arm. I don't think it would make any difference to the cloud lifetimes.
Okay, we'll do Alyssa, Benedict, and then Blakely.
I'm just going to channel Thomas Henning for a second. So before you came to the Harvard meeting, Thomas told us that the analysis of the GMFs that they looked at shows that the star-forming properties of those is the same as giant life of clouds. And then Catherine, of course, has found that their aspect ratios are nowhere near as elongated as the long clouds you were showing. So I would be careful, and I would say the GMFs are just the long end of the GMC tail, and they don't seem to be particularly in any special place. I think it's only the super long ones that we call bones that are similar to those.
Okay.
So I was wondering about your feedback, because in your movie it looked very sort of steady state, quiescent. When I look at more modern simulations of galaxy formation, they typically have these real blowouts where you see a ton of gas being blown out in essentially a cluster of supernovae that explode into pre-empty medium. And given that you actually modeled this at very high resolution, I was surprised that you did not see that.
I'm guessing it's just different initial conditions, so these are quite low surface density galaxies, pretty quiescent conditions, so quite different from galaxy formation.
It's different from starburst, so the blowouts are in the starburst.
Oh.
No, they happen in normal Milky Way flights.
Oh, in Milky Way.
It's because we've clustered supernovae, but when they explode into bubbles, then you really push the gas out very far, and you see it in the movies.
Well, isn't it like when you do those simulations have it where, because I'm guessing here the way that she's parameterizing the supernova is just based on stellar mass, whereas I think some work now is finding that when you have clustered supernovae, it actually enhances an momentum injection, so she may not be capturing that.
Yeah.
Yes, no, I haven't made any
Yeah.
attempt to cluster them.
Yeah,
Yeah,
it's just
fine.
like if you have 5
Yes.
supernova going off, and that's 5 times
Yes.
10^51,
Yes.
whereas those it's like there's an enhancement.
No, but that's maybe we should talk later. But I thought they would be naturally clustered in your simulation because the resolution is so high. You know, because you actually resolve this much better than most of these other simulations.
Because they go off at
Anyway, we can talk about this
But,
later. This is
yeah,
really different.
yeah, there are people that I think have applied the same physics to quite different environments, and it might be worth checking what differences they saw and whether they were able to produce those outputs with the same physics that they've used in sort of quiescent galaxy simulations.
Blakely?
So I'm wondering if, so you did runs with and without feedback, does that at all change your cloud lifetimes? I mean, you had a pretty broad range, so they weren't all on a crossing time. It's kind of what maybe most were on a crossing time, but actually you had some that were much longer lived. Did including feedback change that at all?
Yeah, the feedback changes it massively. I didn't actually compute the same plot for without feedback, but my expectation was that there would be a lot more very long-lived clouds. I mean, you can see in the simulation that they're just not being dispersed. And I think the work of Elizabeth Tasker's group, they've done similar simulations which don't include feedback, and they also find a population of very long-lived clouds. So it's a bit like bimodal.
Great, and I guess another question is there's group by Mark Krumholz, there's work by Mark Krumholz's group that suggests that including feedback actually can reduce the velocity dispersions. And they're using very different sorts of simulations, grid-based simulations. I'm wondering if you've thought about that or thought about comparing the SVH simulations with other kinds of grid-based flows to see if there's actually a code difference, like numerical difference.
Yeah, we have compared with the grid code for the whole galaxy, and Well, we found that you had to be more stringent with the resolution requirements for the grid code than is commonly done. I think Mark Krumholz's group do use the same resolution requirement as what we did in this work, but they produced quite similar results. But that was just a fairly simple calculation. We haven't tried the same thing on like a higher resolution section of galaxy or something.
Yeah, that could be a really interesting comparison. See what's going on with lots of instructions.
Do you have a question?
Yes, it's all about feedback. The question is whether, you're paying attention to the most rare events that are the most powerful, the supernovae,
Yeah.
but there is an energy injection from stars, either in the form of radiation or winds,
Yes.
that is
Yeah.
more steady. So the difference would be that instead of rare events that inject 10 to 51 ergs with some efficiency, you
Yes.
would have a more widespread injection of energy, and that would change dramatically.
The simulations of section and spiral arm, I have run them with energy injected over a longer time scale, not over a particularly long time scale, only like 5 megayears or so, rather than tens of megayears, which you ideally want to do. But it didn't change the results much. But if we had a prescription where stars escape from, or stars no longer within a cloud, then that might change it more radically.
It does happen.
Yes, yeah, that does.
Okay. Well, actually, I'm going to ask one question and then we'll end it. But so the nice thing too is like you're able to kind of see the lifetime of the like clouds and then also the clusters and stuff, and you get the steeper slopes. So by comparing, so there's like a lot of debate about how long star clusters actually survive. Are they typically born in bound or unbound?
Yeah.
Associations and so on.
Yeah.
And you have one group that says feedback destroys clouds, or destroys clusters within 10 megayears, and then there's no mass, but there's no mass dependence. And you have other group that says it's galactic. It depends on the global properties, so it's dynamics, not feedback, and so on. So with your simulations, what camp you fall in?
No, well, actually, my next plan is to perform more detailed simulations to try and address that question. So I might not offer an opinion.
I think it's going to depend on the feedback that you include, because that, depending on the different modes of feedback you include, will actually change. Like, for example, like Avi was saying, once you have stars, then you just have radiation and outflows, etc. Dump energy and momentum in, whereas you have a delayed start with supernovae. Sort of thing. Okay, sorry, that was like, I've only been to so many of these colloquiums, but I've never seen so many questions. That's great.
Oh,
so we had a lot of really interesting people. So let's thank Clare again.
Thanks for the short answers that enabled all the questions.
Oh, right.
It's not that many, there's only 45 of the things you can start with. There's only 45.
I just wanted to give you a very short, maybe interest.
No, but I would say you have